Welcome to my channel. Today, we meet again, and in this video, we will analyze in detail the plane crash of American Airlines Flight 191. We will delve into the events and factors that contributed to this tragic accident. Join me as we explore and gain a deeper understanding of the consequences and lessons learned from this incident. The 25th of May, 1979 was a bright blue, sunny day in Chicago, Illinois, a day filled with the promise of summer. For millions of travelers across America, it also heralded the start of a weekend filled with relaxation, fun at the park, and perhaps a thought or two for the nation's fallen soldiers. That weekend America would mark Memorial Day. And most workers could expect Monday off. At Chicago's O'Hare International Airport, 258 passengers, some of them on their way to a publishers' conference, others headed for the beaches of Southern California, boarded American Airlines Flight 191 to Los Angeles, a big silver three-engine McDonnell Douglas DC-10. Only a few years had passed since the DC-10 became the center of a global scandal over the poor design of its cargo door, a flaw which had caused one of the deadliest plane crashes of all time in March 1974. Some passengers didn't pay much heed to the plane's reputation, but others did. One man, originally booked on Flight 191, asked his trip organizer to put him on a different flight after he found out that he would be flying on a DC-10. He could not have known that his decision would save his life. By the time the passengers and crew boarded Flight 191 at the gate at O'Hare, the story of its destruction had already entered its final chapter. All the traps had already been set, the fate of the plane and its occupants already sealed. The story in fact began years earlier and hundreds of miles away from the sprawling airport in Chicago. In the mid to late 1970s, McDonnell Douglas became aware that a set of bearings, located inside the pylons which attached the DC-10's No. 1 and No. 3 engines to the wings, were wearing out sooner than expected. In order to fix the problem, McDonnell Douglas issued a pair of service bulletins instructing operators to replace the bearings at their convenience. Complying with the service bulletins would require removing the pylons from the wings in order to access the bearings. The engine pylon is a relatively simple and unassuming object, several meters long and made of metal. It has almost no moving parts and exists only to hold the engine in its proper position forward of and below the wing. Engine pylons rarely require any sort of maintenance, a fact which posed an obstacle to airlines wishing to comply with McDonnell Douglas's service bulletin. Removing the engine and pylon was a complex and time-consuming task that was not part of any existing routine maintenance procedure, and the airlines were forced to find time for it while the planes were in the hangar for unrelated reasons. American Airlines, one of the largest operators of DC-10s, decided to carry out the work on the bearings when each plane went in for its C-check, a yearly session of thorough inspections and heavy maintenance during which the aircraft needed to be on the ground for an extended period. But the airline already had good reason to believe that replacing the bearings would be exceptionally arduous. In 1978, American Airlines performed contract work on several DC-10s on behalf of a foreign carrier, which had asked them to bring the planes into compliance with the two McDonnell Douglas service bulletins concerning the pylon bearings. The manufacturer's recommended procedure called for mechanics to first remove the engine from the pylon, then remove the pylon from the wing, a requirement which American Airlines felt was unrealistic, because it took hundreds of man-hours and involved the removal of no less than 79 different connections. On the other hand, if the engine and pylon could be removed together as a single unit, then the process involved only 27 connection points, saving nearly 200 man-hours of labor. Engineers at American were already aware that United Airlines had used this method to drastically reduce the time and effort involved in complying with the service bulletins. But while United used an overhead hoist to raise and lower the engine and pylon, American Airlines opted for something even cheaper and easier, a forklift. The tricky part of raising and lowering the engine pylon assembly using a forklift was that the two parts together weighed more than 8,100 kilograms, and even the most skillful forklift operator could only adjust the height of the forks in increments of 6 millimeters or more. To make matters even worse, the center of gravity of the engine pylon assembly lay nearly 3 meters forward of the pylon's forwardmost attachment points. All these factors meant that the process of detaching the pylon and engine, lowering them to the floor with the forklift, and then raising them back up to reattach them had to be performed with the utmost care. One slight miscalculation of the center of gravity, one tiny shift of the forks, and 8,100 kilograms of metal could slam into the underside of the wing. American Airlines managed to carry out this procedure on the foreign airplanes without causing any damage. However, its maintenance engineers found that it was easier to do the work if some of the steps were performed out of order. The pylon is basically connected to the wing by 3 sets of attachment points, 2 at the front, and 1 at the rear. The original procedure for detaching the pylon asked mechanics to remove the front attachments first. But with the engine still attached to the pylon, the stress on the forward attachment points was too great to remove the pins, and the problem could only be alleviated by disconnecting the rear attachment point first. While this made the pylon easier to remove, it also turned the forward attachment points into a rudimentary hinge. If the forks were lowered too much following the removal of the aft attachment point, the heavy engine would cause the entire unit to rotate around the forward attachment points, sending the aft end of the pylon slamming upward into the underside of the wing with a force of more than 9,000 kilograms. Despite the risks involved in this procedure, and the difficulties that mechanics experienced while trying to carry it out, the airline was still using the same method when the DC-10 registered N110AA came in for its annual C-check in March 1979. At the American Airlines maintenance base in Tulsa, Oklahoma, engineers set about bringing the plane into compliance with the manufacturer's service bulletins, including those related to the pylon bearings. As they had done several times before, they positioned the forklift beneath the engine's center of gravity, removed the attachments, lowered the assembly to the ground, carried out the repairs, gave it a cursory inspection, and finally prepared for the trickiest part of all, putting the pylon back into its mountings. At some point during the process of reinstalling N110AA's left engine pylon assembly, the pylon shifted and struck the bottom of the wing. When and how this happened is not known with certainty. But it might have occurred during a shift change, or when the forklift ran out of fuel and briefly sat idle. This forklift was known to bleed hydraulic pressure, and the forks would drop by about 2.5 centimeters every 30 minutes when the engine was off, easily enough to shift the engine pylon unit around the forward attachment points and push the rear end of the pylon up into the wing. When the pylon collides with the wing in this manner, the brunt of the collision is absorbed by the pylon's aft bulkhead. The bulkhead, a stiff metal plate spanning the interior cross-section of the pylon, normally attaches to a clevis on the bottom of the wing, but removing this connection was the first thing the mechanics did when they started disconnecting the pylon, and the last thing they would do when putting it back together. Without the bolt joining the bulkhead to the clevis, the bulkhead could be forced farther upward until the clevis impacted the upper flange of the bulkhead, as seen in the above animation. On N110AA, this impact severely dented the upper flange and created a 25 cm crack right across the top of the bulkhead. Incredibly, no one noticed. No one heard the sound of the impact over the general hubbub inside the hangar, and inspectors didn't spot the crack because it occurred after the inspection was completed. The mechanics screwed the pylon back in place and went home, completely unaware that the internal structure of the pylon had been fatally compromised. With a 25 cm crack through the aft bulkhead, the remaining life of the pylon could be measured in weeks. Every time N110AA took off, thrust loads passed through the weakened bulkhead, resulting in rapid metal fatigue. The crack grew steadily over the next 2 months, creeping outward in both directions, until it reached a length of 33 centimeters. At this point the entire pylon was hanging by a thread, one more load cycle and it would fail. That final load cycle turned out to be American Airlines Flight 191 on the 25th of May, 1979. 258 passengers and 13 crew boarded the plane, strapped themselves in, and prepared for the 3.5-hour flight to Los Angeles. Little did they know that Flight 191 would barely even make it past the end of the runway. In command that day was 53-year-old Captain Walter Lux, a veteran pilot who was type-rated on at least 8 different airliners and had more than 22,500 flight hours under his belt. Assisting him were 49-year-old First Officer James Dillard and 56-year-old Flight Engineer Alfred Udovich, who together possessed an additional 24,000 flight hours. Their experience alone would have gotten them out of many sticky situations, but unfortunately, not this one. At 15:02 that afternoon, the O'Hare Tower controller cleared Flight 191 for takeoff on runway 32 right. American 191, underway, Captain Lux replied. It would be the last time they spoke to air traffic control. With First Officer Dillard at the controls, the DC-10 thundered away down the runway, powered by its 3 big General Electric CF6 turbofan engines. They hit 100 knots, then passed through V1, decision speed, and continued onward to VR, rotation speed. Lux called out, "Rotate," and Dillard pulled back on his control column to lift the plane off the runway. It was at precisely that moment that disaster struck. Unable to withstand the takeoff load, the damaged pylon aft bulkhead split into several pieces, ripping out the aft connection points. Held to the wing only by the forward attachment pins, the entire number 1 engine and pylon unit started to rotate as the engine thrust propelled it forward and upward. In the blink of an eye, the engine folded back over the top of the wing and fell away behind the plane, tumbling down the runway in a shower of sparks. Inside the cockpit, Captain Lux uttered the word, "damn," and then the voice recorder went dead. From the tower, controllers watched in amazement as Flight 191 lifted off from runway 32R with its left engine completely missing. "Look at this! Look at this," a controller exclaimed. "He blew up an engine. Equipment. We need equipment. He blew an engine." The DC-10 climbed in a level attitude for 15 or 20 seconds, then it started to bank to the left. "American 191 Heavy, you want to come back, and to what runway?" the tower controller asked. There was no reply. "He's not talking to me," the controller said to someone in the tower. As controllers, pilots, and hundreds of travelers watched in stunned disbelief, the DC-10 kept banking left until it was flying on its side, streaking past the end of the runway at a height of 300 feet with hydraulic fluid streaming from the damaged left wing. Within seconds, the plane started to turn inverted. "Yeah, he's gonna lose a wing," said one of the controllers. There he goes," someone exclaimed. With a tremendous boom and an earth-shaking roar, American Airlines Flight 191 slammed into an open field 1,600 meters beyond the end of runway 32R, angled 21 degrees nose down and banked 112 degrees to the left. The plane shattered instantly into thousands of pieces, sending a wave of disintegrating debris tearing through an aircraft parts warehouse, several Quonset huts, an auto repair shop, and a junkyard before coming to rest at the edge of a mobile home park. A huge fireball, visible from the terminal at O'Hare, unfurled into the bright blue sky as the plane's full load of jet fuel ignited. In the mobile home park and the nearby warehouses, people ran for their lives, fleeing what one witness later called a rain of fire falling. As firefighters hurried to the scene of the crash, they already feared that no one could possibly have survived the horrific impact. When they arrived, those fears were sadly confirmed. The largest remaining piece of the plane was one of the badly mangled engines. Everything else had been reduced to charred rubble, scattered through the field and smeared across the burning facades of the warehouses, where the hulks of cars lay tossed about within a sea of flame. Unfortunately, save for 2 badly burned employees of Courtney Velo Excavating, a company operating out of one of the warehouses, rescuers found no one to save. In fact, there wasn't a single whole human body. It was obvious that all 271 passengers and crew aboard Flight 191 had died instantly when the plane struck the ground. It would be several days before recovery crews found the bodies of 2 more people who died on the ground, a truck driver for Courtney Velo, found still in the cab of his truck, and Andy Green of Andy's Auto Service, found underneath the car he was working on when the fireball tore his shop asunder. With 273 people dead, the crash was by far the worst aircraft accident to occur on U.S. soil, a grim title which it still holds today, 42 years later. As photos of the final seconds of Flight 191 spread across the front pages of newspapers around the world, investigators from the National Transportation Safety Board descended on Chicago O'Hare for what would be one of the biggest investigations in the agency's history. From the first hours after the crash, one thing was certain: the DC-10's left engine had separated from the plane during takeoff. There could be no doubt about it. The engine, the pylon, and a 1-meter section of the leading edge of the left wing were still lying on runway 32R. Following the separation of the engine, the plane flew for just 31 seconds, steadily banking to the left, before it dived into the ground. But the DC-10, like all airliners, is capable of climbing normally after losing an engine. To explain how the loss of the number 1 engine could have led to a catastrophic crash, investigators needed to look at the effect of the failure on other aircraft systems. The most immediate consequence of the engine separation, apart from the loss of thrust, was the uncommanded retraction of the outboard left wing slats. The slats are panels which can slide out of the leading edge of the wing to increase its capability to generate lift, enabling flight at lower speeds during takeoff and landing. On the DC-10, the slats were held in the extended position for takeoff by hydraulic actuators. But the separation of the engine severed the hydraulic lines connecting the slat control valves for the outboard left wing slats to their associated actuators. With no local hydraulic pressure to hold them in the extended position, aerodynamic forces overcame the actuators and forced the slats to retract. When the left wing outboard slats retracted, the other slats did not retract, creating an asymmetric lift condition. Calculations showed that with the outboard slats retracted and the engine missing, the left wing would cease to generate lift below a speed of 159 knots. This was the wing stall speed, the speed at which the angle of attack, the angle of the wing relative to the airstream, reached the critical point. At this critical point, airflow separates from the wing and becomes turbulent and disorganized, leading to a catastrophic loss of lift. As it turned out, the pilots would have run right into this critical airspeed simply by following established procedures. The checklist for an engine failure on takeoff instructed pilots to climb out at V2, takeoff safety speed, until reaching 800 feet, then lower nose and accelerate. The checklist told pilots to use their calculated V2 speed because it was a known value already designed to ensure stable flight following an engine failure. But on Flight 191, V2 was 153 knots, lower than the 159 knots at which the left wing would stall. By following the checklist and letting their speed drop to V2, the pilots unknowingly doomed their plane and everyone on it. Indeed, the flight data recorder revealed that Flight 191 began turning to the left as soon as it decelerated below 159 knots. At that point the left wing stalled and lost lift, while the right wing, which still had all its slats extended, continued flying, resulting in a left roll. The pilots attempted to turn right using the rudder and ailerons, but these controls would have been useless if the left wing wasn't generating lift. At the moment of impact, Captain Lux and First Officer Dillard were applying full right rudder, full right aileron, and full nose-up elevator inputs, but their efforts were in vain. To recover control, they would have needed to push the nose down until their speed rose back above 159 knots, at which point the plane would have rolled out of the turn without difficulty. So why didn't they do this? One possibility was that a hydraulic failure robbed them of their ability to manipulate the controls. But while hydraulic fluid was seen spewing from the wing, the flight was too short for any of the hydraulic systems to have suffered an appreciable loss of pressure due to this leakage. Indeed, all the flight controls were working right up until impact. As it turned out, the reason why the pilots couldn't regain control of their stricken plane didn't have to do with the hydraulics, but with the design of the DC-10's electrical system. Like all airliners, the DC-10's engines generate electricity to supply the aircraft's electrical system. When an engine fails, so does its generator, and the associated AC generator bus will lose power. If such a failure is detected, a device called the AC tie bus will activate to tie the failed AC generator bus to one of the other generators, restoring power to systems which rely on the failed generator. But if a fault is detected with the AC generator bus itself, a circuit called the bus tie relay will open instead, isolating the failed bus from the AC tie bus and preventing an electrical malfunction from spreading to the rest of the system. This was what occurred on Flight 191. As the engine broke away from the wing, numerous wires were severed, creating transient short circuits which tripped the bus tie relay and isolated the number 1 AC generator bus. This bus powered a number of aircraft systems, including the cockpit voice recorder, as well as all the captain's instruments, the slat position computer, and the captain's stick shaker stall warning. The failure of these systems directly led to the pilot's inability to recover control. Because of the failure of the slat position computer, the slat position indicators in the cockpit went blank, and the slat disagree warning, which would have informed the pilots that some of the slats had retracted, never went off. Therefore, the pilots could not possibly have known that they had a slat asymmetry problem. As far as they knew, all the slats were still extended. The second nail in their coffin was the failure of the captain's stick shaker. At the time, it was not required that both pilots' control columns be equipped with stick shaker stall warnings, and only the captain's side had one. A stick shaker for the first officer, which would have received power from a different electrical bus, was sold as an optional extra, but American Airlines had opted not to buy it. As a result, the stick shaker never activated. And without the slat disagree warning to tell them about the partial retraction of the slats, the pilots would have assumed that the plane would stall at the slat's extended stall speed, which was comfortably below V2. The cumulative effect of these failed warnings was that the pilots never realized that they were in a stall, nor could they reasonably have concluded this from the indications which were available to them. However, while it is widely believed that the presence of a second stick shaker would have allowed the pilots to detect the stall and save the plane, this is not actually true. The DC-10 stall warning computers only received slat position data from their own side of the airplane, there was no crossover. Because the slats only retracted on the captain's side, the first officer's hypothetical stall warning computer would not have known that any of the slats were retracted, and consequently his stick shaker wouldn't have activated until the plane reached the slat's extended stall speed. This speed was much lower than the speed at which the stall actually occurred, and in fact the plane never decelerated enough to reach it. Only by restoring power to the slat position computer and the captain's stick shaker could the crew have received a stall warning at the correct speed. The only way to have restored power to these failed systems would have been for flight engineer Udovich to manually reconnect the number 1 AC generator bus by flipping the emergency power switch. However, this switch was located not at the flight engineer's station, but on the overhead panel above the pilots. Even if he had recognized the need to activate it, a very big if, he would have needed to get out of his seat, walk across the cockpit, and flip the switch, all in the middle of an extremely dynamic emergency in which multiple critical systems were failing. Investigators felt that he could not reasonably have been expected to do this during the 20 seconds or so before the plane went out of control. A series of simulator tests proved that the failure of the warnings was causal to the accident. After being briefed on the nature of the emergency, pilots who faced a simulated engine separation and partial slat retraction were easily able to maintain control and come around for an emergency landing. However, they universally agreed that without the warnings, no pilot could have understood the situation quickly enough to prevent the crash. Because of these findings, the NTSB heavily criticized several aspects of the design of the DC-10, which featured an unacceptable lack of redundancy. The lack of a stick shaker for the first officer, while not uncommon at the time, was a relic of an era when the captain was the supreme authority in the cockpit, a belief which by 1979 was already on the way out the door. Investigators felt that the first officer's stick shaker should have come standard rather than being sold as an optional extra, even though this was not technically required. Secondly, many other airplanes had mechanical locks to prevent the slats from retracting in the event of a hydraulic failure, but the DC-10 did not. Additionally, good design principles hold that warnings should have backup sources of power and data so that they don't fall silent at the moment of greatest need. And finally, designing the stall warning systems to only take slat position data from one wing, rather than both, was quite simply a lazy design. It is not hard to provide data crossover, and the safety benefits are significant. Most likely McDonnell Douglas designed such a crude stall warning system because the DC-10 had a perfectly good natural stall warning in the form of severe pre-stall buffet. A stick shaker was only required because of a couple of edge cases where the buffet wouldn't give warning far enough in advance, and Douglas likely viewed the stick shaker primarily as a means of fulfilling regulatory requirements rather than a system which was critical to the safety of the airplane. Unfortunately, in this case it was safety critical, because the stall experienced by Flight 191 resulted in little to no pre-stall buffeting. Despite the criticism levied at McDonnell Douglas, the party most clearly responsible for the crash was American Airlines. The crack in the left engine pylon's aft bulkhead occurred because of the airline's practice of removing the engine and pylon as a single unit using a forklift. Although it was faster, this process was imprecise, finicky, and prone to errors. In fact, before performing the procedure for the first time, American Airlines maintenance supervisors had asked a McDonnell Douglas engineer whether it was all right to remove the engine and pylon together, and the engineer told them not to do it. However, McDonnell Douglas didn't have the authority to police the way airlines were maintaining its planes, and American Airlines ultimately decided to go against the manufacturer's advice. The labor costs which could be recouped by using the shortcut were simply too good to pass up. As it turned out, American Airlines was not the only carrier using this method. Continental Airlines also removed its DC-10 engines and pylons as a single unit using a forklift, and they too suffered damage to their engine pylons as a result. In 1978 and again in 1979, Continental found cracks in pylon aft bulkheads. The airline determined that the cracks were the result of maintenance errors and repaired the bulkheads. But damage incurred during maintenance was at that time considered the airline's private business, and Continental did not report the incidents to the Federal Aviation Administration, nor was it required to. In fact, the FAA didn't even want to hear about maintenance incidents. The agency was concerned mostly with damage incurred during operations. And although the FAA did require airlines to report major repairs and alterations, there was no agreement in the industry as to what constituted a major repair, and Continental didn't think its bulkhead repairs had qualified. Because Continental Airlines did not report the incidents to the FAA, nor was there any means of disseminating the findings to the industry at large, American Airlines never found out about Continental's experience. The FAA inspector assigned to American Airlines Tulsa Maintenance Base also had no idea that the airline was using a procedure which could potentially damage the airplane. He had not observed any pylon maintenance, was unaware that American Airlines was removing the pylon and engine as a unit, and in any case had not been requesting the details of the airline's maintenance procedures since 1977. It was his impression that the replacement of the pylon bearings was a minor repair conducted in accordance with an FAA-approved service bulletin, and that he had no reason to apply further scrutiny. In the immediate aftermath of the Flight 191 disaster, as it became clear that cracks in the pylon had caused the crash, authorities finally took action. 3 days after the accident, the FAA ordered emergency inspections of the engine pylons of all DC-10s in the United States. To the horror of all involved, the inspections found cracks in the pylon aft bulkheads of 6 more DC-10s, 2 at Continental and 4 at American Airlines. One of these cracked bulkheads was experiencing metal fatigue and probably would have failed eventually, causing another accident, had it not been caught. In light of these findings, on June 6, 1979 the FAA ordered the grounding of every DC-10 in America, until such time as it can be ascertained that the DC-10 aircraft meet certification criteria. The DC-10s remained grounded for more than a month until the FAA rescinded the order on July 13, citing the fact that the cracks were the result of a particular unsafe maintenance practice rather than a design flaw with the airplane. The planes flew again a few days later, now under the protection of an FAA directive which declared any DC-10 legally unairworthy if the engine and pylon were removed as a single unit. Further developments did little to exonerate American Airlines. It turned out that American Airlines maintenance supervisor Joe L. White, who worked at the Tulsa maintenance base, had been writing memos to his superiors about the dangers of the engine removal procedures since 1978, warning that they could cause damage to the pylons, but the airline ignored him. When a case related to Flight 191 landed in civil court, American Airlines tried to get White to deny any knowledge of the memos. When he refused, the company fired him. During the trial, the airline only produced one of White's memos, allegedly written 4 days before the crash, even though according to White's own records, he had written numerous memos, and the last one was submitted 24 days before the crash, not 4. The U.S. District Court for the Northern District of Illinois ended up penalizing American Airlines for destroying documents related to the accident, although it was not stated whether the White memos were the documents in question. In addition to the prohibition of the dangerous pylon removal technique, numerous other changes were made in the wake of the crash. The FAA issued a series of airworthiness directives mandating actions which included the installation of 2 stall warnings, one for each pilot, which draw data from both angle of attack sensors and all the slat position sensors, and mandatory inspections any time a pylon is removed from a DC-10. The crash also led directly to the creation of a voluminous regulation known as the Instructions for Continued Airworthiness. These rules completely overhauled the way airplanes were maintained in the United States. Whereas maintenance had until that point been an airline's own private matter, under the new rules airlines became formally responsible for ensuring that their airplanes adhered to a standard of continued airworthiness, that is, that the specifications by which the airplane was originally certificated continue to be met throughout the life of the airframe. The problem at the time was that airlines were conducting all kinds of repairs and inventing their own maintenance procedures without a standardized system to determine how those repairs and procedures might alter the assumptions that were made during the plane's certification. For example, the DC-10 certification assumed that the separation of an engine and pylon on takeoff was a 1 in 10 billion event, and other systems on board the plane were designed based on that assumption. But American Airlines' in-house practices significantly increased this probability and undermined the basis on which the plane was considered safe. Despite this, American Airlines was not required at that time to seek FAA approval of its maintenance procedures. Following the introduction of continued airworthiness rules, all of that changed. Now there are clear boundaries defining which maintenance procedures require FAA approval. Obtaining this approval also requires the airline to submit a continued airworthiness analysis which proves that their repairs will not compromise the assumptions on which the airplane was certificated. At the same time, by standardizing the process of reporting major repairs and eliminating the tendency to treat maintenance-related damage as an internal issue, the new rules paved the way for more centralized tracking of maintenance problems throughout the industry. This has allowed airlines to receive reports of problems from other airlines, the FAA, and manufacturers through a variety of reliable channels, ensuring that information about technical difficulties reaches everyone who needs to know it. Looking back more than 40 years after the crash of American Airlines Flight 191, it is indisputable that the tragedy led to profound changes that have made flying considerably safer. But for many who remember the crash, it marked a moment when their faith in the safety of airline travel was abruptly shattered. Many to this day recall the fact that the plane was equipped with live cameras showing the view from the cockpit, cameras which may have given the passengers front row seats to their own imminent demise. For others, it was the last straw for the troubled DC-10, even though American Airlines was primarily responsible for the crash. Later in 1979, 2 more DC-10s crashed in Mexico and Antarctica respectively, causing further panic about the aircraft type, even though both accidents were caused by human error. For several years following the 3 crashes in 1979, public distrust of the DC-10 was so high that sales flagged and McDonnell Douglas struggled to make back what it had spent on the plane's development. During this period, the DC-10 picked up its now infamous nickname, Death Cruiser, a moniker which it never managed to shed. Despite its reputation, however, the Flight 191 disaster was the last time a DC-10 was involved in a crash which had anything to do with its design, and it went on to have an accident rate no worse than that of the beloved Boeing 747. Today, the place where Flight 191 came down is still an empty field, the mobile home park is still home to hundreds of families, and the strip of land where the warehouses once stood is now a storage lot owned by XTRA Lease Trucking. A memorial now stands in a park several kilometers away, but the site of America's deadliest air disaster remains just as much an unremarkable slice of Midwestern exurbia as it was on that fateful day in 1979. However, as so often seems to happen, the site is soon to become a freeway interchange, and every day hundreds of people will drive over the exact spot where 273 people died, most of them without thinking about the indescribable horror which took place there. As the crash fades into history and the world churns ever onward around that sad stretch of dirt and concrete, it is our obligation not to forget the lives that were lost on the long and winding road to where we are today. Thank you for joining me on this journey of analyzing the crash of American Airlines Flight 191. Your support and engagement have been invaluable throughout this video. I appreciate all the feedback, comments, and discussions we've had along the way. I hope that this video has provided you with a deeper understanding of the circumstances surrounding this tragic event and has sparked further interest in aviation safety. Remember, learning from such incidents helps us strive for safer skies. Please feel free to leave any additional comments, questions, or suggestions for future videos in the comments section below. Your input is highly valued and helps shape the content of this channel. Thank you once again for being a part of this community and for your unwavering support. Stay safe and see you in the next video.